Hi, and welcome back to another lesson in the Mechanics Physics video series. Today we'll be discussing acceleration. In linear kinematics, the first 5 equations are what are used exclusively for us to solve for the various equations of motion, be it speeds, velocities, acceleration, displacements, and times. Mechanics equations on the reference table numbers 1 and 2 deal with averages, and the instantaneous motions, these incorporate acceleration in formulas 3, 4, and 5. Let's take a look at an example. Here's an acceleration exploration. A car traveling at 8 meters per second accelerates at a rate of 2 meters per second squared for 10 seconds. Make a table of the motion, graph the data from the table, and determine the distance traveled for the whole trip by finding the area under the line. Parts 1 and 2 of this problem ask us to make a table and graph the data. So, starting with a table, on the x, y axes, we know that time is always an independent variable and shows itself on the x-axis exclusively. And in this case, we're talking about speed on the y-axis, because speed divided by time is acceleration. Let's just check the reference table for that. And we see it, equation 2, acceleration is equal to the change of speed divided by time. So what does an acceleration rate of 2 meters per second squared mean? If we write it out this way, 2 meters per second squared, we really see that the numerator is a speed of 2 meters per second per 1 second. So the positive means that the car gets faster by a speed of 2 meters per second for every second that ticks away. So let's look at a 10-second interval, 0 to 10 seconds. Now we know that the initial speed of this car is 8 meters per second, and at a rate of 2 meters per second increase, 8 will go up to 10, 10 will go up to 12, all the way up to 28 in the 10 seconds. So a car that started off at 8 meters per second that increases its speed by 2 meters per second for every second that the clock ticks away will see a speed increase of 2. 8 plus 2, 10 plus 2, 12 plus 2, all the way until you get to the end of the time limit, which is 10 seconds. Let's take a look at the graph. If I have the x-axis going from 0 seconds to 10 seconds, as I have here, 0 to 10, and an initial speed of 8, increasing by 2 until it reaches a speed of 28, I get the following graph with plots pointed like this: 0, 8, 1, 10, 2, 12, 3, 14, etc. When I plot those points and graph the line, I have the equation y equals 2x plus 8. By the way, this r squared equals 1 is the correlation coefficient in Excel, which proves the percentage of accuracy of our points. And since this is 1, it's 100% accurate as an equation. We know that this car is accelerating in the forward direction at a constant rate. The fact that it's a constant rate is the reason why we have a straight line slope. Let's take a look at this graph and compare it to one of the graphs on the 5 motion graphs to verify. You will recall the 5 columns. The V versus T right here shows us that when V is on the y-axis and T is on the x-axis, we see that the constant slope of a VT graph is a uniform acceleration. Let's find the distance traveled based on this graph alone. So we know that the distance traveled is equal to the area of the rectangle plus the area of the triangle that are underneath this VT line. The rectangle represents the distance traveled due to the initial speed, and the triangle's area represents the added distance traveled due to the acceleration. Recall that the equation of this line, y equals 2x plus 8, Using the equation of a line, y equals mx plus b, we can see how y equals 2x plus 8 actually fits into the equations that we find on the reference table. In particular, equation 3, VF equals VI plus AT. We're going to put the AT first and the VI last because it will match the form of the equation y equals mx plus b. So on the y-axis is the speed, the slope is the acceleration, the x-axis is the time, and the y-intercept is actually the original speed or the initial velocity. Plugging in the data that we have, we see that VF equals 2t plus 8. 2 is the acceleration, 2 meters per second squared, and 8 is the initial velocity right here. When we add up the areas, we will notice that the area of the rectangle is 10 seconds times 8 meters per second, which gives you 80 meters. And then the area of a triangle is 1/2 base times height. 1/2 of 10 seconds times 20 meters per second. And where did that come from? You could see here that the speed at 10 seconds, you get 180 meters when you add them all together. And the final notes on this: an increasing graph in any shape is getting higher in the first quadrant. A constant slope is a straight line y equals mx plus b, where the slope is a constant number. And for this example, it is the acceleration of 2 meters per second squared. The area under the line of a VT graph is always the distance traveled. In closing, it's always helpful to remember the 5 motion graphs chart. The top D versus T row shows you the relationships between distance and time for some object at rest or in cruise control forward and backward motion, acceleration, and deceleration. The VT row shows you the velocity versus time relationship, and when you have a flat slope, that's 0, and therefore there is no acceleration. But you see in acceleration there is a positive slope, and deceleration there is a negative slope. So a positive 2 meters per second squared acceleration corresponds to an object that gets faster by 2 meters per second for every second that it travels, and a negative 2 meters per second squared acceleration would be that it gets slower by that 2 meters per second. And these are the accompanying graphs. They always go together. There is no mix and match, cross on diagonals. It's always above and below go together. And there you have it. This is how an acceleration problem is solved, by first making a table, graphing the data, and determining the area under the curve for the distance traveled. I hope you enjoyed this video. Thank you for watching, and we'll see you in the next video.